All right, so here, a couple other examples of the tangent line. Remember, we got a number of different derivatives. We should be able to do this stuff regardless of what kind of function we have. We could have the quotient rule, product rule, chain rule. We could have trig functions, okay? Here, we want the equation of the tangent to y equals tangent of x at the point where x equals pi over 4. Okay? Now, what point is that? Pi over 4, what's tangent of pi over 4? You masters of the unit circle.
I know the coordinates are square root 2 over 2 and square root 2 over 2.
Good. Those are the coordinates. So 1. Very good. Tangent is sine over cosine, right?
Oh.
Because on the unit circle it's root 2 over 2, root 2 over 2. So sine and cosine are the same. So tangent must equal 1. And actually we'll use that fact here even. Tangent is sine of x over cosine of x. Alright? Now, to get the slope of our tangent line, we need the derivative. Does anyone happen to recall what the derivative of tangent is? Secant squared. Good memory. If you don't remember, that's okay, because you guys know the quotient rule, right? And you guys know that the derivative of the top is cosine times the bottom is another cosine minus the top times the derivative of the bottom. Derivative of cosine is a negative sine. So I'm going to put the sign here. I'm going to throw the negative out in front, so now it's plus. And that's all over cosine squared. Now, my top is sine squared plus cosine squared. What does that equal? 1. Okay? So this is 1 over cosine squared, which happens to be secant squared. Now, the reality of this is, this next to last step is probably the one that we're going to use. Because, I don't know what secant of pi over 4 is, but I do know what cosine of pi over 4 is. Okay? So, for my slope, what's the 1 over the cosine squared of pi over 4? What's the cosine of pi over 4? Root 2 over 2. Okay? So this is 1 over root 2 over 2, and that's squared. Well, root 2 over 2 squared is 2 over 4, which is a half, and 1 over a half is 2. So there's my slope. My slope is 2. Now I can get my equation. The tangent line, y minus 1, equals the slope times x minus pi over 4.
Are we going to use this formula all the time? Are we going to use y equals mx plus b at all?
Whatever you want. I use this a lot, but whatever you're comfortable with, you can use. So this one, when we simplify it, we distribute the 2. So we have y equals 2x minus pi over 2, and then we add the 1 to both sides. And you can leave it like this. Okay? I know that's kind of awkward looking to us to have a minus pi over 2 plus 1 as our y-intercept. Okay? But better that than to get decimals and round. We'd rather just keep it exact. Okay? Any questions about our tangent? Okay. So, two other applications. So they're kind of cool. And this next one, we're really going to dig deep into our pre-calc honors and algebra 2 honors bag of tricks in order to get this, okay? Find the coordinates of the points where the tangent to y equals x cubed plus x plus 2 at 1, 4 meets the curve again. Now let's illustrate what this is actually talking about. We have this function. I know the y-intercept is at 2, and I know it's cubic, all right? So I don't know exactly what this looks like, but maybe it looks something like this. Okay? And I know at the point 1, 4, you know what, let me... maybe it's like something like this. I'll just make it easier to draw. At the point 1, 4, let's say that this is our point 1, 4. I have this tangent line. But one thing we need to understand about our tangent is that our definition of tangent, we need to kind of adapt to the fact that we're not dealing with circles anymore. With circles, it only ever hit the circle once. Okay? In this case here, it hits the function, but because our function kind of curves back around, it is possible that our tangent line will hit the curve at another point. In this case, over there. See that? So what we want to figure out is, what is that point? Okay? Where are we when we get back on the curve? You could think of it kind of like if you're off-roading on a car and you kind of slid off the side of the road. Here you're driving along and here's a curve and you missed the curve. But hey, since you're off-roading anyways and you know the road comes back around here, you just keep driving in a straight line and you know you'll hit it at some point, right? So that's kind of what we're doing with our function and our tangent here, okay? So, to do this, think about what we're actually doing. We're finding the intersection of a line and a curve, which means we're going to do what? How do you find intersection points? On your graphing calculator. Set them equal to each other, and what we're doing there is we're solving a system, right? We're solving a system of equations. Okay? So, we've got to solve our system here. But we know one of the equations in our system, that's the original function. What we don't know is what the equation of that tangent line is. Okay? So here, we've got to find the equation of the tangent line, then we can solve the system. Okay? So, let's do that first. Alright, the tangent line. Okay? dy dx, this is a polynomial, so that's easy. 3x squared plus 1. I already know the point of contact. It's 1, 4. We were given that, so that's kind of nice. How am I getting my slope for my tangent line? Finding it with the x?
Plugging the x into the...
Good. Plug in the x. 3 times 1 squared plus 1. So the slope is 4. And based on our drawing, that makes sense. Okay. See a positive slope there. So now my tangent line, I know the slope, I know a point. I know it's y minus 4 equals 4 times x minus 1. And you'll notice here, my drawing's a little bit off because we actually get y equals 4x. That tangent line should be crossing through the origin, but that's okay, it was just a sketch to begin with. Alright, so here is our tangent line, and here is the function itself. We need to find the intersection point by solving the system of equations here. And like Evan said, we're going to set those equal to each other. Okay? They're both equal to y, so if we set them equal to each other, we can then solve the system. So let's do that. 4x equals x cubed plus x plus 2. Now, if we're solving this, so we want to get it equal to 0, first we have x cubed minus 3x plus 2. Problem is, there's not a real good way of solving that, unless we remember we already know one of the answers. What's one of the answers? 1. That point 1, 4 is an intersection point, right? So I know x equals 1 is an answer.
You factor out an x minus 1.
We are going to factor out an x minus 1.
So if we're looking for an answer, if x equals 1 is an answer, so how does that work?
Well, we got to factor that out. Can anyone tell me how we would factor that out? Because we can't do factoring by grouping on this one. That doesn't work. There's really no good way that we've learned to factor this other than one.
Something like long division or something.
By actually doing the division. This is where, remember synthetic division? This is where that comes in handy. Okay, this is going way back in our pre-cal honors.
So what do we do?
So let's do the synthetic division. We need to divide the x cubed minus 3x plus 2 by x minus 1. And if you remember, you can do long division if you really like that. But since it's just an x minus 1, remember we could put the 1 in the box here. And then we list the coefficients. So we have a 1x cubed. Don't forget the placeholder for the x squared. So we have 0x squareds minus 3x plus 2. And then we work through our process of adding down and multiplying over. So 1 plus 0 is 1. Then we multiply by the 1 that's in the box. Now we add down and get 0 plus 1 is 1. We multiply over and it's still equal to 1.
Wait, we multiply
By the 1 that's in this box here.
1 by 1 we get 1, then we should add them up, right?
Then you add down, multiply over. Add down, multiply over. So we add down again. We multiply that by a 1 and get negative 2. And we add down again, and it's a good thing we got 0, because that tells us that we do actually have an answer. Okay? That was the remainder, and the remainder should be 0 in this case. But that tells us here what goes in the parentheses. Okay? What was it?
X squared plus x minus 2.
Perfect. X squared plus x minus 2. And now we're actually able to factor that. X minus 1. This factors into an x minus 1 times an x plus 2. Alright? So 1's a double root. That's nice. That's not really going to give us our result, though, that we're looking for. What we're looking for is that last answer there. Because x equals 1 or negative 2. So this point up there must be the point negative 2 something.
Do x negative 1 and x negative 1 cancel out? Or
No, because we're not dividing. It's just
Oh, right,
like
we're
it's
just
a double root. or has multiplicity. Okay? So, now that I know x is negative 2, I can plug that in. Where do I plug it in? In where?
Either one.
Either one, yeah. Save yourself a little work and plug it into the line. 4 times negative 2 is negative 8. You could double check your work by plugging it into the original function as well. Okay? Negative 8 minus 2 is negative 10, plus 2 is negative 8. We get the same thing whether we plug it into the line or the original function. But that right there is the point that we're looking for, negative 2, negative 8. That's the location where our tangent line will meet the curve again. Okay? Now, notice here the calculus wasn't really the hard part, right? The calculus was pretty easy on this one. The challenge, though, can be using that calculus to get what you need and then going back and doing that older stuff, okay? Finding the intersection point, doing synthetic division possibly, okay? There may be instances where you have very, very complex functions and you end up needing to just use technology to help you solve the system. That'll work too if you have the calculator available on that one. Okay? Alright, last one. This one is kind of a different situation, but it's similar to what we just did. The difference is this: we don't want to hit the function again. We actually want to hit another point that's not on the curve. Alright, you might be like, well, what in the world, what's the point of this? Think of it like this. The tangent tells us the path that we would take if, let's say we were traveling along this and we just let go right here. We stopped trying to stay on this curve, we just let go and it flew off. It would go along the tangent. You know, it's kind of like if you swing something around your head and you let go, it was going in a circular motion, and the direction it goes is going to be whatever the tangent to your circle was the moment you let it out of your hands. All right, the ancient sling that they used to hunt with. Okay, they.
Shot put.
Huh?
Shot put.
Not shot put. The hammer throw actually is similar to this. If you've seen the hammer throw, they spin around and around and around, and then they let it go. But they used to hunt with slings, and they were just like a rope. It was strapped to your wrist, and it had a little pouch in it, and you'd hang on to the other side of the rope, and you'd swing it around, and you'd let it go at a certain moment when the tangent of the circle you were spinning it at is aimed right at what you're trying to hit. And it's amazing that anyone can hit anything with those things, but some people are really, really good. That's kind of the idea here. This is what they use when something's orbiting the moon and they want to get it back to Earth. They got to hit a certain spot in the Earth's orbit so it'll actually catch on the Earth's gravitational fields and not slam into the Earth, but then they want it to like orbit a little bit before they do a re-entry, or maybe not, you know. So they have this target that they're aiming for. They've got to know exactly when to release so that their tangent line will be aiming at that point. Okay? Because it takes a lot of fuel to readjust and get back on target. So if they can release right at that moment, they'll hit their point. Okay? If you've ever seen Apollo 13, that's what they had to do because they were out of fuel, basically. They had enough fuel to get out of their orbit, but if they did it at the wrong moment, they'd miss hitting the Earth's atmosphere and bounce off.
Did you see Hidden Figures?
I haven't yet.
They actually like show her doing this calculation like on a board for like
Do they?
finding the right point. Yeah. for
That's
the
cool.
tangent, yeah.
That's cool. We'll have to, maybe we'll get that clip or something. All right, so how do we get this? All right, well, this is where you kind of have to think about what you're trying to find, okay? We want, we need to find the line, and it's going to intersect this curve at this point, okay? So you'll notice the first thing they did, they identified this point as some random number a for x, and then since we have x squared, they plugged a into the function and got a squared for the y coordinate. So they have a generic point on the curve using a, and there's nothing special about a, they just chose to use a. All right? Now, if you think about this, I know that I want to hit the point 2, 3. So if I have 2 points on this line, what can I figure out? The slope of that line. Okay? So let's do that. The slope of this line would be a squared minus 3 over a minus 2. Right? That's going to be the slope of the tangent line I want.
Which one are you using? Like, where do you get the?
That's just my slope formula. y2 minus y1 over x2 minus x1, or delta y over delta x. Okay? So that's all I'm doing there. I'm just using my slope formula. How else can I find the slope of that tangent line?
Could you find the derivative of that and then use slope-intercept form?
We actually don't have to use slope-intercept form, but let's get the derivative. What's the derivative of x squared? 2x. So at the point a squared, what's the slope?
2a.
The slope is going to be 2a. Right?
How did you get a?
Well, that's the point we wanted at, right?
Yeah.
So that's the point we want, so it's got to be at 2 times, we're plugging in a for x.
Okay.
All right, we just don't know what a is yet. However, what can we do at this point? Set them equal to each other. We know they both represent the slope that we want. They both represent the slope that we want. So we know 2a has to equal a squared minus 3 over a minus 2. All we have to do now is solve that equation for a. All right? And there actually will be 2 different answers. Okay? We have a quadratic, right? There's going to be 2 different answers. So watch this. If I multiply by a minus 2 on both sides, I get 2a squared minus 4a equals a squared minus 3. If I get everything over to the left side, I'll have just a 1a squared minus 4a plus 3 equals 0. So that factors, right, into a minus 3 times a minus 1. So my 2 answers are 3 or 1. I might say, well, how in the world are we getting 2 different answers? Well, what do you think?
The slope is either 0 or 1.
No. A is either 3 or 1.
Okay, so the slope is 2 times whichever one of those is right.
That's correct. Okay? Now watch this, because actually both are right.
That's trippy.
Okay? Watch this. If A is 1, let's say that would make this point what? 1, 1. Okay? Here's my line with a slope of 2, right? Has a slope of 2. Well, if A is 3, what point would that put me at?
3.
3, which is over here, 9, which would be like way up here, right? And the slope, here's the continued x squared graph. The slope would equal what?
6.
6, all right? So from 1, 1, the slope equaled 2. From up here, it's much steeper, but notice there, that's the 0.39, and our slope was actually 6. Both of those are valid answers.
Where did you get the slope from?
I went back and plugged it into my slope formula. Either this or this. So, I know the slope is 2 times A. Okay?
They both find this numbers, they're not negative.
Yeah, they're both correct answers here. There's actually two different possibilities. Now, we have, this is find the equation of the tangents. Did you notice that little S there? They were actually telling us that there'd be more than one answer from the external point. So at this point, all we have to do is actually use the slopes that we know and use the points that we know in order to find our equations, okay? So this first one here, the slope is 2. I know I want to hit the point 2, 3, so I'll use that in both. Y minus 3 equals 2 times x minus 2. So y would equal 2x minus 4 plus 3 is a minus 1. Okay? My other line up there hitting at 3, 9 has a slope of 6. So if I do y, again, I want to hit the point 2, 3. So y minus 3 equals 6 times x minus 2. I'd have a y equals 6x. Negative 12 plus 3 would be a minus 9. Okay? So those two right there are both tangent lines that would get us to hit that point.
So what you did in the last one, you plugged in the 2 and 3, right? Point 2, 3.
Yes.
And you plugged in both of those.
Yes.
You found
The two different lines. Okay? This line here would be this one. This line down here would be this other one. Okay?
So they're tangent lines.
Yeah, those are the two different tangent lines that would both hit that. And actually, if you think back to your geometry, this makes sense. If you remember in geometry when you talked about circles and you were looking at the tangent from a point outside the circle, there were always two tangents, right? There's one and there's one. In fact, you even had a theorem that for a circle, not necessarily for this, but for a circle, the distance from the point to the point of tangency was always equal on both of those. Okay? So you've seen this before, just not in the context of something other than a circle. Okay? So that's pretty cool. That's pretty cool. Any questions? Good.